way of bundling functionality together that you might need. I'm going to jump over to the Python 3 documentation, and in the documentation, there's a link there for the library reference, and that has a lot of the information in it that I'm after. And I'm going to scroll down here just quickly. All this stuff, all these things that are written in monospace font here, these are all modules. These are all pieces of functionality that have been written for you already. Stuff like dealing with dates and times, dealing with math, and so on. Lots and lots of stuff in here. CSV files. I just wrote a Python script 2 days ago to help me deal with CSV files when looking at GCA test data for different cohorts. I use the CSV module to read in that CSV file, comma separated value file. So all this stuff is here. Tons and tons and tons and tons of things. Look, there's an HTML parser in here. I once used Python to write a scraper that went to my router because my router was losing signal. And if I logged into my router with a web browser, I could actually see this table. It would print out a table that would show all the signal strengths on all the channels. But I wanted to automatically record that every minute so that I could plot a graph and animate showing the signal drop so that my ISP would finally help me fix it. So I used that. I used an HTML parser. I went and downloaded the web page from my router and used the HTML parser to find the tables in it, extract the information out of the tables. Really useful. So lots of stuff is in here. But how do we use it? I'm going to just choose a library. Let's choose math because I know it has stuff we can use in it easily. Where was that? Math. I lost it. I'm going to jump in here. Mathematical functions. So we see we have the module name here, math dot. Turns out modules get imported as regular objects in Python, just like we were making our own class and instantiating objects yesterday. Modules are objects too. So you can access things within modules by using the dot operator, just like this. So let's choose one of these. A factorial, how about that? This is a factorial of a number. And if you don't remember what factorial is, it's the number times the number minus 1 times the number minus 2 times the number minus 3 all the way down to 1. 6 times 5 times 4 times 3 times 2 times 1 is 6 factorial. We could write a loop to do that, but check it out. It's built into math. And so how do we use that? I don't need this anymore. How do we use that? We can say import math, and now we have access to that object. Now I can say math dot something. So let's print out 6 factorial, see how big that is, and it's 720. 6 times 5 times 4 times 3 times 2 times 1. We were able to use that because we imported the module. Now, if I don't import the module, it shouldn't work, but I have a feeling that Colab is already importing modules for me automatically, probably, but let's find out. Yeah, it didn't matter in this case. But if I were to try that in a real REPL out here, why is my screen formatted so weird here? That's weird. Oh, scroll down. All right, whatever. Let me jump into a real REPL right here. And I say math.factorial 6. It's gonna, oops, 60, one more time. It's gonna tell me math is not defined. I've got to bring that thing in. Now I can do math.factorial and get an answer. So in Colab and also in Code Signal, math is automatically imported for you. A bunch of things are. But if you need something else, you can always explicitly import it like this. If you're writing your own software that's not in Code Signal, not in Colab, then definitely import all the things you need. By importing math, that allows us to use all the math stuff. There's one more variant of this. I'm going to choose another math function here. What's another fun one? Integer square root. How about that? Is anybody else thinking, yeah, integer square root, that's fun. That's the most fun thing. No? All right. We can bring in specifically this so that we don't have to type math dot every time. So there's a slightly different import line that you can use. From math import I square root. And when you use this version, you don't have to put math in front of it anymore. The integer square root of 49. Whoops, did I get that wrong? I could have sworn that was going to work. From math import this. Maybe I can't import that because it's not an object? Maybe I'm wrong about this one. It's been a long time since I've used this particular way of writing that. Does anybody see what I'm doing wrong with that? Or maybe I'm about to learn something. There's a module, the square. Weird. I'm Googling now and it's telling me that other people are getting other things. Square root. Oh, that worked. Is I square root not a thing? Math I square root. New in 3.8. Oh man, I wonder if I'm not running version 3.8 in there. That must be it. I was losing it for a second. I'll bet you this version of Python that we're running right in here is not 3.8 plus. I'll bet you that's what's going on. And it says here that the integer square root is new. Look at this one. LCM, new in 3.9. They're introducing new stuff all the time. Parath says, I think Python runs 3.7, or Colab runs 3.7. All right. Anyway, those are the two big ways of importing things. I kind of prefer being explicit about it like this, just so people know exactly that I'm using something out of a particular module. But there's really nothing wrong with doing things this way either. This is commonly done. What I have in line 2 is commonly done, especially with modules that have really long names, because people get tired of typing out huge things every single time. It's not so bad with math.factorial, but some of the modules do have large names and they do have large functions inside them or large named objects inside them. But that's the extent of it. If I could add to this. You can also import your own modules. If you have a file called foo.py, I could do this. All the details about importing your own modules get a little bit complicated because you can put them together in packages and there's like this init.py file and stuff like that. I don't want to get into it too much. It's enough just to know that you can bring in stuff from the library that you find in the documentation here. And it's worth giving this a skim just to see what's in here because there's all kinds of crazy stuff. What do y'all think? Importing modules, straightforward enough. Like I said, I don't want to get into writing our own modules, but it is possible to write your own modules in Python and then reuse that functionality elsewhere. Questions? Thumbs up, thumbs down? I got 2 thumbs up, 3 thumbs up. I can only see 4 videos at once, so it's all right. Brendan says, I imagine this would be a way to get React style modularity. And I'm going to kind of hand wave on the answer because modularity, definitely, that's what it's doing. React style, your all's React skills are stronger than mine. So I'll take your word for it on React style. All right, cool. Let's jump into stores key value pairs. We didn't talk about this yesterday, did we? Am I having deja vu? All right, good. After a few years, it all starts to blend together. All right, so I like to think of these things as like lists, which of course are arrays, except the index can be numbers or strings or other types. So it kind of operates the same way. But if I code one of these things up, it might remind you of something. So I'm going to make a dictionary called D, why not? And here's how you make a dictionary. You use squirrely braces like that, and you put some keys in here and some values out here. Why it keeps wanting to indent me farther here. Yeah, look at this. Once of you are already noticing this. One of the big ways programmers learn new things is, hey, what does that remind me of? This remind me of anything I've seen before. And the more things a problem reminds you of, the more ways you can think of to attack it. So yeah, this is looking kind of familiar. If you're coming from a JS background, this looks like JSON. Quite a bit like it. There are some restrictions, though, compared to JavaScript objects, because a dictionary, while a dictionary is an object in Python, it's not used in quite the same way necessarily as in JS. Python might be a little more flexible than JS, like Brandon's saying, in terms of what you can use as a key. Like you can use other objects as keys in dictionaries. It's pretty impressive. If you've come from JavaScript, you're probably used to doing something like this. There's key foo right here on the dictionary, right? D.foo. Let's make it work. Dict object has no attribute foo. That doesn't work quite right. So like I said, the dictionary is an object, but the way you extract information out of it or put information into it is not necessarily the same as JavaScript. We have got to use bracket notation for this. Not only that, but we have to use bracket notation with quotes if that thing's a string. Now we're getting stuff out of it. So here's how we extract information. Out of a dictionary by key. Dot notation doesn't work for that. Notice I used a different type here. 10 works. We can actually put floating point numbers in there too. That works just fine. We can also set items in a dictionary. Just like that. That'll add one in there. Let's see, you can't index into the dictionary either directly by number. You can only index into the dictionary by the key. There's something really cool about dictionaries that I'm going to say once now, and we'll talk about more a couple other times. No matter how many things are in the dictionary, it always takes the same amount of time to look one of them up. Let me say that again. If the dictionary has 10 keys in it, it takes a certain amount of time, like if you're measuring it, it takes a certain amount of time to look a key up. If the same dictionary has 20 billion keys in it, it still takes the same amount of time to look something up. It's like magic. No matter how much stuff is in there, it always takes the same amount of time to look it up. We call this order 1 time complexity, or constant time complexity. And we'll talk more about that later. And it's awesome. If you have a thing that takes the same amount of time to look stuff up in, no matter how much stuff is in it, that's pretty cool. There's some trade-offs there in terms of memory. And when we get to hash tables week, we'll actually look at the dictionary under the hood, and we'll see how that works. We'll see how it's possible to make a data structure that has constant time lookup characteristics. Christopher, there's not a limit where it breaks down, other than the amount of memory you have on your computer. Maxwell, when I say time, I mean it in terms of big O time and not, actually in this case, I'm talking about big O time and literal time. But more on that in a little bit. And it turns out the tech behind making that happen for a dictionary like this is pretty simple. It's kind of amazing. One of my favorite data structures because of its simplicity and the performance impact. But more on that when we get to it. All right. So this is kind of getting and setting basics on dictionaries, but I kind of want to talk also a little bit about how we can iterate over these things. So great, we have a dictionary, we can add things to it, we can get things out of it. There's actually a, I can't remember if it's a method or delete or something. You can remove a key from a dictionary if you don't want it in there anymore. We can look that up though. Delete. Is it .pop on a dictionary? Is that, let's see here. Built-in functions, int, float, list, tuple, stir, mapping types. Here we go. Blah, 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 blah. Making new dictionaries. set, key in, key not in, iterate, clear to remove everything, copy to make a shallow copy, get to get an item, items, keys, pop. Keys in the dictionary. It is pop. Look at that. Keys in the dictionary, remove it. Otherwise, return whatever the default is. If the default is not given and the key is not in the dictionary, key error is raised. All right, so we should be able to delete something from the dictionary with pop. Let's just add that. Print new key. Let's, oops, new key. What am I doing? New key. I'll bet this returns the value, 3490. But let's get that out of there. And then lastly, I'll print the entire dictionary, because Python will print the whole dictionary out for you, just like this. And we see we've deleted this key, and it's no longer in the dictionary. Cool. All right. Let's do some iterating, because I want to be able to do some things like iterate through a dictionary, see everything that's in there. And it would also be nice to be able to sort the information that's in the dictionary. And that's not totally obvious. Should we do sort yet? Yeah, maybe we should wait. Or should we? I don't know. I know I was going to talk about it again in a couple weeks, but I think we have time probably. All right, I'm going to copy my dictionary down there again. Let's just see what's in there. Let's use a for in loop, see what happens. So looks like using for in goes through by key. So we could get the value by looking in the dictionary at that key. There's a similar thing. Uh-oh. Am I still here? Can somebody give me a thumbs up? My internet is warning me on all kinds of things.
You went away for a second, but you came back.
All right. A glitch in the matrix. I was saying, remember how enumerate gives you back the index and the value at that index when you enumerate through a list? There's something similar for dictionaries. The items function. It'll take a dictionary and iterate over the keys and values inside that. Let me give myself a little identifier here so we can differentiate our output a little bit better. Let me actually type in some real words. What do we got here? :1, where did that come from? Is everything lined up now? Key value. Items is not defined. Oh, sorry, it's not enumerate. I can only do so much out of memory, apparently. It's d.items. My mistake. It's a method on the dictionary object. There we go. So for this one, we're getting the same output, but we've just acquired the key and the value a different way. So both of those can be useful. Here's a question for you. If I were to run, if I were to run this loop right here, let me change this. And I'm going to do this, and we're going to print that out. What kinds of things do you think we'll see printed here? Does anybody have a guess? So I was doing a destructuring assignment here to get keys and values back, but if I just print out the one thing that D items returns, what are we going to see? Key value pairs as an array, tuples. Let's run it. 3. There we go. It looks like it's a bunch of tuples. And the 0th element in the tuple is the key, and the 1th element in the tuple is the value. Which makes sense because in this line right here, we do a destructuring assignment. It takes these two things and unpacks them into K and V, just like that. All right. So we've got a way to iterate through the dictionary. We've got a way to look stuff up. Oh, I have one more thing I want to add. But before I do that, what do we think? What do we think about the iteration? Is that straightforward enough? Other questions about it? Of course, dictionaries, lists, they can be composed together. You can have a dictionary that has lists in it. You can have a list full of dictionaries. All these data structures can be put together like Legos to solve different problems. How do we feel about this stuff? Thumbs up. Christopher says, do you find that developers have a few data types that they really like and they just use them for everything? Oh, I don't know if I would go that far, but I would say that a few data types correspond to like 90% of the data type usage that's out there. So knowing like a handful of things and how to use them well, like dictionaries and lists and sets, maybe, that gets you a lot of the way towards solving a lot of problems in kind of the way that having a hammer, a screwdriver, and a crescent wrench gets you a lot of the way to solving a lot of problems. They're just tools that are good for a lot of things. A lot of problems use them to get solved. But that said, every developer I know is not afraid of switching to a different tool to solve a very specific problem. So some of them might be looking at a problem and think, you know what this means? This needs a min heap. That's what we need to solve this problem. Barely ever use a min heap for anything, but that's what's needed in this case. A specialty tool for a specialty job. Good questions. Brendan notes it's easier to iterate than JS. Gosh, it's been a while since I can't even remember how to do it in JS. Oh, something about getting the, I don't remember. All right, one more operator I wanted to point out here was test if something was in a dictionary. And what else do I have? What other names do I have? Key 1 is in there. Yeah, key 1 in D. We can use the in operator right here to see if it's in there. In also actually works with lists. It's just it's slower with a list as the list gets longer and longer, whereas it's the same speed in a dictionary, even if the dictionary gets bigger and bigger. So this is saying true, key 1 is in the dictionary. All right, so this is kind of dictionary warm-up. This is a powerful thing that you can use. And remember how I said that it doesn't matter how many things are in this dictionary, it always takes the same amount of time to look up a key. It also always takes the same amount of time to test if a key's in there. So when you're solving these problems, keep this in mind. When you solve a problem and you're passing all the tests, except some of them are timing out, some of them are taking too long to run, think to yourself, is there some way I could load this data into a dictionary and take advantage of the fact that dictionaries are fast at looking up data in large data sets? Is there some way I can do that? And so sometimes it makes sense. If you have a big list of data, sometimes it makes sense to load that into a dictionary in a certain way so that you can query against the dictionary in a big hurry. We'll talk more about that several times, but keep that in mind when you start seeing timeout errors on some of the problems, that dictionaries can often come to the rescue. Christopher says the speed of a dictionary, does it have to do with how the items are stored in memory? Kind of. It's still stored in a list under the hood, but we have an indexing mechanism in a dictionary to tell us which array index to look in for a particular key. So Josh is going next level, enumerate dictionary items. That's going to print out the index of each dictionary element that it's gotten to in D items, and then there's going to be a key value pair afterwards. All right, let's so that's kind of whirlwind introduction to dictionaries. Let's take a break here, and when we come back, oh, I said Ooper Revisited was going to be first, so I lied. When we come back, we're going to do a quick revisit of Ooper, just to keep that fresh in your head. And then I want to talk about how variables work under the hood in Python. Yesterday, I had mentioned that in Python, they often refer to variables as names, that it's just a name for a particular object. And we kind of looked at how that worked with self and cat and dog in that example yesterday. How we could have multiple names for the same object, multiple variables referring to the same object. We're going to dig into that a little bit more and see how it ties in with variables being references to objects, which is a concept we're going to use a lot in the next 2 weeks. We're going to have tons of variables that refer to other objects, and we're going to use that ability to reference one object from another to build complicated data structures with that. So it's an important piece to get in terms of understanding how variables relate to one another. And a little piece of bonus information on Christopher's question here. What's my main focus as a developer? Java, Python, C++, etc. I kind of pride myself on being a jack of all trades kind of developer. So in my programming career, I've done C and C++ and Java and Perl and Python and what else? What are some of the other languages? There's just more in there. JavaScript is definitely in there. And I haven't programmed professionally in Go or Rust, but I've spent time learning both Go and Rust and Scheme as well. Not really great at Scheme, but worked at it a while. Erlang. Ruby, I would have loved to get into it. I never did. COBOL, I've never programmed anything in. I did take a Fortran class in college, though. And I have, Juan, on that note, I have written assembly language that I hand assembled with a pencil, and then I typed in the hexadecimal numbers on a hex keypad into a computer and had it run the program. So I haven't written anything in binary, but I have written something in hexadecimal just once. I like Scheme as a Lisp language, Ian, but I really don't have that much of a preference. I only went with Scheme because I was studying from a book called The Structure and Interpretation of Computer Programs, which is a famous book from MIT, and they use Scheme in that for all their programming challenges. When I did that hexadecimal programming thing, I was sitting in on a class with a friend. He was actually taking the class, and I was just hanging out. And so I wasn't really paying much attention to the lecture. I already knew how to program in Z80 assembly, which was what they were teaching. And so in this little crazy box of a computer that was like a hand-built computer, I wrote a program to make the LED lights like go back and forth, you know. That was it. I was just killing time in the lecture. All right. Speaking of killing time in the lecture, let's take a break and then check out The Secret Life of Variables when we come back. See y'all soon. And don't forget, it's useful to get up from the computer during this time. Howdy, everybody. Okay. Let's see. Quick review of Ooper and a check-in. See how things are going. See how we're feeling about understand and plan, and are we spending enough time understanding and planning a problem before we launch into it? I know I'm laboring this point, but how's everybody feeling about that? Are we getting better at spending more understand and plan time? Got at least one nod there. All right. And what's your experience? Are you finding that it makes it easier to program or not? Brendan's been blowing through engineering paper. Sweet. Brendan says it makes it way more fun. I love that observation. The reason I love it so much is because in my mind, it's the problem solving that is kind of the most fun part. Like figuring out how we're going to put this thing together. What are we going to do? What's the plan? And then when the plan feels solid, coding it up and having it work, it's like, yeah. Christopher says, saves a lot of time, definitely. Juan says, able to keep track of my train of thought. Brendan says, stuff actually works. Bobby suggests multicolored pens. Oh, I like that idea. I was pretty lucky in my .com job. When the business moved, they got rid of a bunch of whiteboards. They're like, anybody want whiteboards? I'm like, yes. So still on this wall right here to this day, I've got a big old whiteboard, a bunch of pens over here. I use that to scribble out ideas for solving problems all the time. Yeah, good stuff. All right. And if you haven't been spending a lot of time on understand and plan, I'm going to keep hammering away at this. Definitely spend at least 10 minutes doing this on a problem. Set a timer if you have to, and prohibit yourself from writing any code until that timer expires. Spend that whole time understanding exactly what's asked of you to the point that you could explain it to somebody else. And when we talk about interviewing techniques in a couple weeks, that will tie in very nicely. So understand at the point you can explain it to somebody else, and then come up with a plan that you are certain is solid. We're all imperfect, so your plan that you're certain is solid might not actually be solid. Your understanding of the problem that you're sure you have might not actually be there. That happens to me, happens to everybody. But you make your best effort, and that saves a lot of time in the long run. Pseudocoding. I do a lot of that during the plan phase. That's allowed. Nick says, I brainstorm in a text box in Colab and then use that to test snippets of code before writing the main stuff. That is also a totally valid use of writing code. I'm like saying, don't write code during this phase, but I often do that. I'm like, hey, I can take this approach if Python can do this thing. And then I pop into a Python REPL and I just type it in. I'm like, if I do assign A to this, can I run this function? Yes, it works. Great. That becomes part of my plan. Maxwell, I do not use any separate apps for planning, and I have awful handwriting. So maybe I should. For larger scale projects that involve multiple people or multiple teams within the company, certainly there are a lot of applications that you can use for planning out the structure of how the data flows, planning out the architecture of a large scale project. And so for something big, I would use something like that. But as a junior dev, that's probably going to be what your manager or the senior dev of the team is doing, and you'll be implementing parts of it. All right, so remember, understand and plan. But then I'm going to add on to this a little bit. We didn't talk about this much, but execute when you're typing in the code, great. After execute is reflect. And this is an important phase. And if you complete the project, remember I said no Googling for the answer to the project, but if you complete a task and you have it working, feel free to Google for that at that point. Look at your code, think, what could I have done to make this better? But Google around and look at other people's solutions. You have one that works, that you made, but if you Google around for other people's solutions, you can compare and contrast your solution to theirs and cast a critical eye on that. Do you like the way you programmed it better? If so, keep doing it that way. Do you like the way they programmed it better? Then hey, incorporate that stuff. Coding is a creative endeavor, and there's a bit of subjectivity to it. It's that reflect phase where a lot of people improve. So don't skip out on it. You definitely improve with the hard work of understand and plan. That's like the heavy lifting, but you can learn more finesse with that reflect phase. How could I have made this marginally better? How could I have made the code easier to read? Maybe some comments would help. Maybe some blank lines would make it more readable. Maybe some better variable names would make it more readable. Brendan says, I love to refactor at the end. So satisfying. It's like the pressure is off, right? You have a working solution. Now you got to do is go back and polish that thing a bit and make it look good. We'll talk more about that when we get to interviewing as well, because when you submit code to companies, you should make that code look good, just like you make your resume look good. And we'll talk about ways to do that later. All right. Ooper. Let's talk about how variables work. We're going to switch gears a little bit, and I'm going to use my fun little drawing tool again to talk about how items in memory exist and how we refer to them with variable names. Also, we're going to tie this into mutability and immutability. Like yesterday, we were talking about how a list is mutable. That is, you can take that one list and change an element inside it. But a string is not a string is immutable. A string cannot be changed. The only thing you can do is make a new string. You can slice it up, but it makes new strings every time you do it. So we've got these two classes of variables in Python, ones that are mutable, ones that are immutable. The mutable ones are, if I remember correctly, lists, dictionaries, sets, and user-created objects. Let's put that down in notes somewhere just so we have it. Let's see here. I do not need right now, but I do need one of these. I should say they refer to objects in memory, names for those objects. Objects themselves, not the variables, mutable or mutable. That is, they can be read-only or read-write or unchangeable or changeable. But it's important to note that the variable is not what's mutable or immutable. It's the thing that it refers to in memory. So let me put together an example here. I'm going to put, I'll make a variable A that's a list, 1, 2. You know what? Let's start even simpler. I'm just going to make a list 1, 2. That's all. Turns out, amusingly, this is valid Python code. It doesn't do anything. This is just Colab telling me what the value of the last line of the program was. Valid Python, though, which is kind of weird. But what happens in this line is that Python says, oh, you want a new object. We're going to make a new object in memory. And it's a list, and it's got 1, 2 in it. There we go. And so in this diagram, I'm using the circles to represent objects that exist in memory. And so we made that. But we didn't do anything with it at all. Shrink myself, give myself some room here for all this stuff. We didn't do anything with it. We just kind of made it. And then Python's like, well, you didn't actually store that in anything, so you have no way of referring to that. So I'm just going to garbage collect it. And so Python actually gets rid of it because there's nothing referring to it. But let's say we did want to refer something to it. Let's say we wanted to store that in a variable. I keep saying store it in a variable, but really what I'm saying is I want to make a name for this object. I want to make a variable that refers to this object. This is a subtle distinction, but it will help out a lot in the upcoming weeks. So Python makes the object. It's a list with 1, 2 in it, and then it makes a name for that. It makes A, the name A, refer to that object. And I'm going to indicate that with this line right here in this diagram. So right now, there's an object in memory, the list 1, 2, and A refers to that object. All right, now I'm going to write one more line of code, and this is the crux of it. This is the part to pay attention and understand. B is assigned A. That's the line of code. I think we're pretty good on what happens if I do this. The output of line 5. B is assigned A, so B must be like A. So yeah, it must be 2, right? It must be this 2 right here. But now I have a question for you. What has happened with this line of code on line 3? There are kind of 2 options. Option A, we make a copy. Maybe Python made a copy of this. Did it make a copy of that list? Like this? Brand new copy in memory, and then assign B to it? Is that what happened? Or did B just change to refer to the same list that A refers to? Which of those options must have happened? And this is the important part to understand. Turns out in Python, these refer to the same object. There's no copy. And this is true in Python for every single assignment you do. Doesn't matter if you're assigning a number into a thing. It doesn't matter if it's a number or a string. Anytime you do an assignment that's like this, it's going to make a thing refer to another thing. And if that other thing is a reference itself, like B is already a reference, or A is already a reference, B is just going to be a copy of that. Christopher says this concept is language specific, right? And it is. But this model of thinking actually works in a lot of languages. Like JavaScript, Java, they all use similar mechanisms for storing their data. A language like C is a little different because it does make copies of the data. So yeah, it's language specific. But in Java, JavaScript, Python world, this works. And even though C doesn't work like this under the hood, the same mental model turns out to work in C. So Barath notes that a.copy would make a copy. Yes, that is totally true. Let's do that right now just to see it. C equals a.copy. This will make a new list. And so what Python does is first, it executes this part of the code that I have highlighted, a.copy. It's like, oh, you want me to make a new list in memory? Great, we'll make a copy of A in memory somewhere. There you go. Oh, and then we want to save a reference to that. So C is going to be the new name for that. So in that case, we would end up with this. Christina says, so the reason we don't say store into A was because B also holds the same object. Yeah, B and A refer to the same object. And it's unfortunate terminology that I use myself all the time because we have this concept that we're storing a thing in a variable. And mentally, that kind of works out. The mental model works out. So whenever I say in Python, I'm storing something in a variable, that actually means I'm making a variable refer to that thing. Christopher has a great point. You're homing in on it. A and B both refer to the same object. If A and B both refer to the same object, then what happens if I do this? If they both refer to the same object. Let's change B. Let's mutate the thing that B refers to. Change that first element to 999. And then let's print out the first element in A. Check it out. 999. B and A both refer to the same thing. So when I modified B on line 7, we actually changed, whoops, I didn't want to double click that. We actually changed this to 999. So now when I print out A sub 1 on line 9, it's going to print 999 because that's the value that it's referring to. This is not obvious. So if you find it challenging to think about, you're in good company because most people do. But thinking about variables in this way, just as things that refer to objects, this will save your life in this coming week when we talk about data structures that are objects that point to other objects. And it is the same in JS, Brennan. Nick, when you say data frame, what are you referring to? Are we talking about like stack frames? Oh, I don't know pandas, so it's not out of my element. Let's see. Christopher says, so in this case, you might change A to a tuple and then make a list version of A and B. Like we could do that. We could totally do that. Remember, it's not, remember the variable itself, A or B, that's not what's mutable or immutable. You can always change a variable to point to something radically different. You can assign a string into it, then you can assign a number into it. You can always change a variable to refer to some other object. But Christopher, if I'm hearing what you're saying something like, let's make A into a tuple of itself. Oh yeah, if you wanted to prevent mutation. Yeah, if A were a tuple to start with, we would have trouble because this would make it read only. If I do that on this line, line 7, Python's going to be like, you're trying to mutate a tuple, and a tuple is immutable, so no. C equals A.copy. That doesn't even work. Oh, tuple doesn't have a copy attribute. I didn't know that. Well, we should be able to make a new one by doing this, maybe. Yeah, there we go. This also makes a copy, or rather, makes a new tuple from A. And there we go. So line 7, now we're unhappy. And B would have to be made into a list from that tuple if we wanted to mutate it. And then it would be a different object. Since C makes a copy of B before, then C1, yeah, let's check that out. That's a good question. So C makes a copy ahead of time. Let's copy it this way. C makes a copy ahead of time, then we mutate all this stuff. So now printing C, we should still see 1, 2 for C because C is referring to this thing. We made a copy of that list before we mutated it. And so C should still be 1, 2, just like in the diagram. And it is. I can elaborate on this a little bit more, then I'm going to run a couple more examples. You can tell where in memory an object is with a built-in function. There's a built-in function called ID, and you can give that an object reference like A. And this will tell you where in memory that object begins. Memory you can think of as a big array itself. And so it has indexes in it, 0, 1, 2, 3, 4, 5, all the way up to however many bytes you have in memory. I'm hand waving how that works, but basically think of it as a big array. So somewhere in this big array, we have this thing stored. And ID will tell us where that is. So I can print it out and see where A is stored in memory. There it is. Memory is a big array. This is the index in memory where that is. Where the object is that A refers to. It's telling us where this list is. So if I do B is assigned A, and then I print ID of B, what's that going to do? It should be the same thing. It's going to change from run to run, but A and B should both be in the same place in memory. So let's check. They are. A is in memory here, B is in memory here, same address, we call it. So it must be the same object. And yes, Christopher, the size of a variable is flexible in Python under the hood. There's also another operator called is. If you want to see if two things are refer to the same object, you can use A is B, and that will print out true if both these refer to the same object. But here, if we print A as C, we should get a false because C made a new list. So C refers to something different. A refers to this one, C refers to this one. So A is not C. If we run that, we see that it's false. All right, I'm going to run another demo here. Let's bring up another thing. 1, 2. A is assigned 1, 2. B is assigned 3, 4. So we have two different lists here. And let me update this to reflect it. Am I editing already? 1, 2. And then B refers to list 3, 4. So we've got two objects in memory, list 1, 2, a list 3, 4, like this. And A refers to 1, 2, B refers to 3, 4. what am I going to add to my diagram if I do run this line? C is assigned A. What does that add to the diagram? C points at 1, 2. C with arrow to the same object as A. Yeah. So C is assigned A. Great. What if I do this now? So where am I? Am I typing? There we go. What if I run this one now? Now what happens? Now it points at the same thing that B points to. It's almost like we moved C from this one. We moved C over to this one. C was referring to this object, but now it's referring to this object. This is actually kind of a powerful notion. We can have a variable that refers to one thing, and then it refers to another thing later. When we get to linked lists, we're going to use this a lot. So A and B, in my mind, I kind of think of A and B as like the permanent names, even though they're not really permanent. I think of them as the permanent names for these two things. And C is almost like a nickname, because we're bouncing C back and forth between A and B like that. So B refers to this thing, but C is an alias for it now. Both B and C are aliases for it. And we can re-alias C all we want. Let's push it back to A. So C becomes an alias for A. It stops being an alias for B. So we can make up new variable names, as many as we want, to refer to some object. Why am I indented by one space this whole way out? That's weird. So C equals A, D equals A, E equals A. This is just going to make more and more references to the same object. Hold on to that thought. Let's see, C points to B. What if you now say B is assigned A? I probably already lost track of everything. B is assigned A. All right, yeah, I think we're all asking the same question here. We get to that in just a second. Christopher says, this is great, but should we be cautious when taking advantage of this feature? I would say only as cautious as normal, so that you don't introduce any bugs. It's interesting. In the Rust programming language, there are restrictions on this. In Rust, every object has an owner, and you can't actually have two variables that refer to the same object if they both want to change it. Rust will stop you. It's really wild. It becomes interesting to program things. A lot of you are asking, what if at this point in time, at the very end of all this, what if we say B is assigned A? We could also say B is assigned C or D or E, because they all refer to A. It's all the same. But what if we say B is assigned A? That means B is going to point to the same thing A points to, which means it stops pointing to 3, 4 and starts pointing at 1, 2. So if we did that, B is assigned A right here, this is what would happen. Look at that. We've got 5 variables all referring to the same object. What happens to this thing? Yeah, Christopher notes this is garbage collected. What is the garbage collector? The garbage collector is a piece of software inside Python that decides if that memory is needed anymore. Is this list 3, 4 needed for anything anymore? If it's not, it can free up that memory and reuse it for other objects later. And so the way the garbage collector works, again, a little hand-wavingly, the way the garbage collector works is it keeps track of how many variables refer to an object. If at least one variable refers to an object, the object will not be garbage collected. It will persist in memory. But as soon as the number of references to an object falls to 0, just like it has here, then this item gets garbage collected and it's gone forever. And that's okay, because we did not have a reference to it anymore. We had no variables that refer to it. So as programmers, from our perspective, we had no way to ever get that back. If you have an object in memory and you don't have any variables pointing to it, you have no way in your program to refer to that thing. I mean, what would you type? There are no variables that refer to it. It's just gone forever. So as soon as the number of references to an object falls to 0, that object gets garbage collected and reused. Or the memory gets reused, I should say. Garbage collection is a concept and a greater concept called automatic memory management, where the software itself keeps track of, hey, do you need that thing anymore or not? Java does it, JavaScript does it, Swift does it, Rust does it, Go does it. All modern languages tend to use automatic memory management so that you don't have to manually say, hey, allocate that space, and then later manually say, deallocate that space. Leads to a huge class of bugs. The C programming language does not have automatic memory management. But this is why in Python or JavaScript, you're able to just make new objects and then forget about them when you're done. And you can trust that Python will be good enough to figure out which things aren't needed. Now, I've been doing this with immutable objects, but let's do some more examples here with some immutable objects. So I'm going to make a new variable here, hello world. And let's try this thing out. So hello world is that object, and we have a variable a referring to it. And we can do what we've been doing. I can say b is assigned a. This doesn't make a copy of it. It just gives us another variable that refers to the same thing. Just like every straightforward assignment from one variable to another, this is what happens. But what if we want to change one of those letters? Like I could say a sub 1 is assigned an x. What happens if I do this? Error, a new object. In this case, those are both good guesses, good answers. In this case, it is an error. We just simply cannot support the item assignment. We can't do that. If we want a to refer to this with a letter x in the front, we have to build that thing by hand. We have to make a new string. And so I can do that. I can say a is assigned x plus whatever a was from the first element on. So I'm going to slice a right here. I'll slice a from element index 1 all the way to the end. So hello world without an h. And then I'm going to stick an x on the front of it, and the a will be assigned that. And so first Python evaluates the right-hand side of the expression, the right-hand side of the assignment. And it says, what are we building here? Looks like we're building a string. All right, we're building a string. Let's do it. X, and then the rest of the string is a slice of a from LO on. There we go. Great, we built that in memory just like you asked me to. And what's that? You want me to assign that into a variable here? All right, let's do that. So we're going to take variable a and we're going to refer to this. Variable a did refer to hello world before, but now it doesn't. Now we've changed it to refer to this thing instead. But check it out. We've modified a, but look where b still refers. B is still pointing back at that old hello world. It was like A started by pointing to hello world, and then we set B to point to the same thing, so they're both pointing to hello world. Then we changed A to point to something else. This new string that we built. So printing B, what should be the output of line 6? Line 6 should be hello world. Let's find out. Hello world. Without the X. Meanwhile, A should have the X in front. So even with immutable objects, when you do an assignment like this, it makes B refer to the same item as A. Let's use the is operator, make sure that they do actually refer to the same thing at that point. After we reassign A to point to this new string, at that point, it should become false, because now after this assignment, A points to something different than B does. All right, I'm going to pause here for a little bit. Take a deep breath. How are we feeling about this concept that variables are just names for objects that exist in memory? And we can make multiple names for the same object. And when we do an assignment, it's not copying the object. It is just making a new name for the same object. If we want to make a copy of the object, we have to explicitly say, hey, copy that thing, then assign it into a new thing. How are we feeling? So I'm about to give you a preview of what we're doing next week, just so that it sits in your head for the weekend. Got some thumbs up. Brendan says it's logical. So the one takeaway here is, remember, when you assign from one variable to another, you're just making another reference to the same object. You're not actually copying anything. The only time you make a copy is when you explicitly do it. Okay. Let's see here. Let's do this really fast, then we'll take a break and we'll come back and do some time and space complexity stuff. So this is a preview for stuff coming up this week. I'm going to make something here, a new class. I'm going to call it class node. I'm going to make a constructor in this class. And when I construct new objects, I want that object to have a value attribute set to whatever we pass into the constructor. And then I'm going to have a next attribute, which I set to none to start. None indicates no value. None is actually an object in memory. There's one none object that gets made for you automatically. And so I'm saying self.next refers to that none object. And we'll say self.value refers to some value object. And then we're going to wire something together in this way. Watch for a second. I'm going to make a new node with value 1. And so if I print that out, we should get a value of 1 and a next of none, because that's what I initialized it to. So let's give that a run just to make sure. So I made a new variable called head. Head's value is 1, and next is none, just like gets created in the constructor. So far, so good. Now we're going to do this. Head.next is node 2. Next is here. This variable, head.next, I've made it refer to a new node, which is kind of weird. Again, you don't need this for today, but a preview of this coming week. So I made a node, and I made head refer to that. And then I made another node, node 2. Node, did I spell that right? It's right on the cursor, node 2. And then I made head.next refer to that. Actually, let me back this up one step just to make it a little bit clearer. I'll name this node X, node 2. We'll start with that. Node 2 is X. So straightforward enough. Now let's do an assignment. Head.next equals X. So X is referring to node 2. Head.next is assigned X. Remember, this doesn't make a copy. This just means that head.next should refer to the same object that X does. X refers to node 2 right here. So head.next should refer to the same thing. I'm going to draw that with an arrow right here. This is head.next, refers to that. And remember I said none is an object on its own right? That's our default value for next. I'm going to throw none out here. And this is node 2.next right here. This is what we have constructed. This thing is called a linked list. And we'll talk about this all next week. It is a collection of nodes where each node refers to the next node in the list by its next pointer, we call it. And what we'll see next week is we can walk down this list by making a new variable, a variable called cur, for example, for current. And we could move cur from this node to the next one via the cur.next variable. And so we're going to write code that moves this variable down the list until it reaches the end. But that'll be next week. But notice in here that we have objects that we've made. We have references to those objects like head and X. And then we have a .next variable in here inside the object itself. And .next can also refer to anything. I mean, we can, like value and next, these are just attributes on the object. We can set those to any values we want, like 12 or hello, or we can have them refer to other objects. And Christopher, you're onto something here. It's really weird because we've got nodes referring to nodes. Like, where does that end? Isn't it like a spiral of nodes off into infinity? So line 6, I would say, well, let me clarify the terminology a little bit. Line 8, head refers to an instance of a node. X refers to an instance of a node on line 10. And then when we get to line 12, head.next, this is also going to refer to an instance of a node. Line 8 now, yeah. So head refers to an instance of a node. We're adding another instance of a node on line 10. And then inside that first instance, we're adding a reference to the second instance. Right on line 12. This is inside the first instance. The first instance is head. And then inside that, the next attribute, we're setting that to refer to X, which refers to this node 2. But we don't have to understand this today. I'm just kind of priming your brain with it. But did that help answer that question, Christopher? All right. note here, preview for next week. But this is why it's important. This is why understanding that variables are just referring to objects in memory is an important concept, because we're going to have variables that refer to all kinds of stuff. And in particular, we're going to have objects that have variables inside them that refer to other objects of the same type. And so we're going to chain together a whole bunch of these objects, next, dot, next, dot, next, dot, next, dot, next, and we're going to build a list out of it. And that list, the linked list, very famous data type, is going to have some interesting performance characteristics. And we're going to analyze those to see when this data structure is good and when it is not so good. And once again, the overarching goal in CS, the one skill that we're practicing more than any other, is problem solving. We're going to use linked lists as a vehicle to practice this. We could have used anything to practice problem solving, but we chose linked lists for a couple of reasons. One of them is that it's a very famous data structure, and it's good for your general edification to know what it is. So if it ever comes up in casual conversation, you don't say, linked list, never heard of it. So that's one of the reasons. Another reason is that it tends to come up in interviews. So we're going to cover it for those two reasons. But again, remember the primary goal of computer science is developing your problem solving skill. Linked lists, difficult problems, we're just using it to exercise those muscles. All right. Oh man, how did I get to 10:38 already? Let's do a quick break anyway, because everybody's brain's probably full. And when we come back, we'll start with some time and space complexity stuff, maybe just time complexity, and we'll continue on with that tomorrow too. But quick preview about time complexity. This is a way for us to kind of gauge how well an algorithm will scale when the amount of data it has to process becomes very large. So when we look at an algorithm, I want to know, is this going to be fine as the amount of data gets large, or is it going to take longer? If it does take longer, how much longer? So we've already seen with dictionaries that no matter how many keys you put in there, it takes the same amount of time to do a lookup, which is amazing. But we also saw with a list, if you have a lot of keys in there, it takes more time depending on how many more keys you have. And so we're going to look at a way of describing that scaling factor of any particular algorithm. All right, but break now. Let's do a 5-minute break just because I don't want to run out of time entirely. But enough time to grab some coffee, and see you soon. that timer just quit after 1 second? Oh, man. All right. Howdy, everybody. All right. I'm going to bring this page up first. BigOCheatSheet.com. And we'll take a quick glance at this without really understanding it, but then we'll talk about kind of what we're getting at with Big O and complexity. So in general, we're interested in how well an algorithm is going to scale. I'll say this again a couple times. As the number of elements to process becomes larger and larger. And so on this axis right here, it says operations, but you can also think of this as time it takes. And on this axis over here, it's how many elements, how much data we have to process. So as we go right, we're thinking larger and larger amounts of data on this graph. And as we go up, we're thinking more and more time it's going to take. And so these lines that we have here, these are some common ways that algorithms scale in programming. And so we want this line to be as flat as possible. If it stays down here at 0 the whole way, that's awesome. We can put a bazillion elements in there, and the number of operations, the amount of time it takes to run, stays low. But some of these other ones, like the one marked order n squared here, this is atrocious. Like, we barely have to get any elements in there before this line rockets off into the stratosphere. This one, order n factorial, you almost can't get any worse than that. It looks like it's going straight up. It's not, but it's pretty horrendous. So if we had an algorithm that was an order n factorial algorithm, like this one here, we would know that as the number of elements increases, the amount of time that we have to spend processing it goes up really fast. Whereas this one out here, order n, as the number of elements increases, it doesn't go up that quickly. This one has a very modest pace to it. So you can think of these big O's like order n squared, order 2 to the n. You can think of these kind of like classifications. what classification does this algorithm fit into? Is it an order n algorithm, which means it grows modestly? Is it an order 2 to the n algorithm, which means it grows atrociously as the number of elements increases? Let me tell you where this will help you, practically speaking. When the number of elements, in this case, n is referring to the number of elements we have to process. When the number of elements we have to process is small, it really doesn't matter anymore what algorithm you use. Pretty much all algorithms are fast on a small number of elements. Oh, we have to search through 5 things? No problem. We can search through 5 things any number of different ways. And it'll still be fast enough for whatever work you're doing, probably, right? So what happens is you write some code and you write some test data. You write out, 5, 10 records of test data, test your code out, runs fine on 5 or 10 things. You tested all your corner cases. That's all great. It works well. Your algorithm works great. So you push it to production. But the production data set is rather bigger. Instead of having 5 or 10 things in it, it's got 500 million things in it. And now your algorithm that you chose to search through that data set, which worked in the blink of an eye with 5 elements, suddenly is taking a lot of time, like real life wall clock time, to search through when you went into production and you saw that there were 500 million elements in there. So as a developer, it's useful to know how much data we're talking about. I need you to search through some data. Your first question would be like, how much data are we talking about here? And how much time do I have to do it in? Because if the amount of data is small, you can use any algorithm you want to search through it. If the amount of data is going to be very large or is going to get to be very large, then you might have to be a little bit more deliberate about it. Maybe your search that you wrote is order n, but really you need an order log n search or an order 1 search, which is even better. So this will bite you when you have a small test data set and your production data set is gigantic. That's where it comes to get you. A real life story along those lines happened to a developer I know. Okay, it happened to me, I'll admit. I was an intern at Hewlett-Packard Corporate, and I was on one of the databases, and I ran a database query. And it was taking its sweet time to finish. And I was like, oh, it's a big data set. It probably takes a while to run this query. And then about 5 minutes later, we got a phone call from the IT department, called my boss, and said, what the heck are you doing to that production server? And it had become unresponsive, this production server, production database server. And the IT folks had to actually go in there and manually power it off because of a query that I ran. And because the database hadn't been indexed in a certain way, the time complexity characteristics of my query were really awful. On my little test data set that had just a few rows in the table, it was fine. But when I went and ran it on production with a million rows in that table, suddenly the time complexity, because the time complexity was so bad about that query, it just started chugging away on the CPU and the machine had to be bounced, which was embarrassing. Now, if I had indexed the proper columns on that table before I ran the query would have been over like that. It would have been ultra fast. The complexity characteristics would have been fantastic, but I didn't. And whoops. So what do these things mean? What do these categories mean? We're going to talk about, let's see, what should we talk about? I'm going to talk about 2 of them because that's about how much time we have. And we'll revisit this tomorrow. When it comes to this stuff, this is telling us again how well the algorithm scales. So if we remember one thing from today, because this sounds good in an interview, time complexity. Time complexity, also known often as big O. This tells us how well an algorithm scales. If you remember one thing for an interview, this sentence is a good one to remember. It's not how fast the algorithm is. It's not how much time it takes. It's how well it scales. It tells us how much worse it's going to be if the data gets this much better or this much bigger. If I double the amount of data, how much more time can I expect this to take? So scales is the key word here. If you want to impress an interviewer, bring that up if they ask you. And so I want to look at a couple ones here. We'll do order 1 and order n, because I think that's all we have time for. The thing in parentheses here, this can be any mathematical formula at all. But the ones that we saw on the Big O cheat sheet, like I said, these are really common ones that show up in computing. This is also called constant time, and this is called linear time. And we'll do quick examples of both of these. With constant time, this means that no matter how big n is, that is, no matter how many elements there are to process, it always takes the same time. Can't get better than order 1. Linear time, this roughly means if you double the number of elements, it doubles the running time. So see how it's not telling us how the time is one specific thing. It's telling us, hey, as n increases, here's what you can expect. If you were in office hour yesterday, I did a quick example with the Fibonacci sequence that was running in 2 to the n time, which meant that every Fibonacci number it calculated, it took twice as long as the previous one. Not good scaling characteristics. If I'm asking you to produce numbers for me and each one's taking twice as long as the last, it's not going to take very long before I'm going to die, because you're not going to get like to number 40. So constant time is great. Linear time is all right. We had, let's see here. Let's throw some code down here at the bottom. We had already noted that a dictionary gives constant time lookups. Which is nice. So if I have a dictionary and we have a bunch of items in it, let me just make myself a dictionary. It doesn't matter how many of these there are. Which is nice. And we can use the in operator to make that happen. But I'm going to do something a little bit different here. I'm going to throw a list out here. A, B, C, and D. A list does not have those same performance characteristics. It's order n search. That means that if we double the length of the list, it's going to take us twice as long to search it. And interestingly, as human beings, this is our typical way of searching a list, right? If I give you a list of random numbers and I say, is the number 17 in there? You're like, well, I don't know. You look at the first one, second one, third one, you hunt through until you find 17 or not. And if I give you a list that's twice as long, it's going to take you twice as long to search the list if you do it that way, right? Whereas if you have it in a dictionary or a set, it's going to be order one time to look that up magically. Let me see. Christopher, are there any good reference materials falling back for CS concepts that I fall back on for CS concepts? You know, it used to be, yes, but now it's a lot of Googling. I have a book I really like. Oh, this is my second favorite algorithms book. I will post a link to it. Corman's Intro to Algorithms. But somebody else, I think, already posted Grokking Algorithms that went by on the main channel, I think. And that is an exceptional book for starting out. Corman's book is big, it's comprehensive, it's intermediate, it's hard to slog through, but you can slog through it. Unlike other algorithms books that I've seen where I'm like, what are you talking about? There's too much math in here. But I'll post a link to that. And then also, I'll post a link to the wiki where we have the CS reading list, optional reading material for CS, so you can check that out. Maxwell says, should any problem be possible to solve in constant or linear time solution at best? No. There are some problems that you simply cannot do that with. So it's kind of fascinating, but sometimes there's just not a shortcut for figuring it out. For instance, figuring out your way across a map. If a map is a collection of nodes where the nodes are cities and they're all connected by roads, figuring out the fastest way across that map, there's no linear time solution for that. There's no order one time solution for that. There's a very famous problem called the traveling salesman problem. It has horrendous time complexity, and there's no better way to do it. Like, people study and study and study, and once every 20 years, somebody finds like this marginally tiny improvement to it, but nobody's found a faster way to do it that gives accurate results. So typically though, Maxwell, when it comes to optimization and deciding, is my order n solution good enough? Is my order n squared solution good enough? The real question is, does it perform in production well? If your algorithm performs in production well, great. Usually, to switch an algorithm to be a better time complexity involves making it more complicated. And your boss is going to want your code to be as simple as possible, but no simpler. So if you have to do something faster, then do it. But if you don't have to, don't do it. So list is order one search or order n search for a list. If you can get away with using n on a list, like this, then great, go for it. But if you can't, because the list is too long and the times are becoming too slow in real life, then you might want to switch to something else. Maybe load that stuff into a dictionary instead. Don't optimize until you have to, is a general rule of programming. All right. So I'm going to post reading list material, and we're going to revisit this stuff tomorrow. So we did a little bit of time complexity here. Remember that time complexity is a way to categorize algorithms into how well they scale as the number of elements to process becomes larger and larger and larger. And we've seen a couple categories here. Searching a dictionary scales really well. It's constant time, takes the same amount of time to search a dictionary, no matter how many elements there are in it. Whereas a list is different. If the list gets twice as long, it takes twice as long to search. So different scaling characteristics for these algorithms. Tomorrow we can talk about a more formal way of taking your code and figuring out what the time and complexity of that code is. And that's all I got. Any more last minute questions here? I guess one addition I would say to Big O notation is good developers are always thinking about this. Like every line of code you write, every algorithm you put together, you're always thinking about what is the time complexity of this thing? Is this piece of code going to be trouble if somebody pours a huge amount of data into it? Or is it going to run just fine? So we're always kind of balancing out what kind of data are we going to get? How well is it going to perform with that kind of data? Do I have to make this more complicated or not? And it gets easier and easier to do the more you do it. And the key word is scale. Yeah. Measures how well an algorithm scales. If I double the number of elements, does it take the same time? Does it take twice as long? Does it take 1,000,000 times as long? How well does it scale as we increase the amount of data to process? Also, if you get better at Big O and you can pull it off in an interview, it's a great thing to drop. Like if they ask you to code something up and you code it up and then you're like, but this is an order n squared solution. There might be a way we can optimize this to get order n out of it. And you're right about that. Interviewers will be like, whoa, because that's a step above what they're expecting. So it's a great way to impress if you get good at this stuff. All right, gang. I will see you all on the help channels. Remember, you're the ones doing the heavy lifting here to practice this problem solving. Every second you spend doing it is experience points in the bank, regardless of whether or not you're actually getting the answer. So keep hammering away at that. That said, we've got tons of help available on the help channels. So if you get stuck, remember the 20-minute rule, get stuck fast, get unstuck fast on the help channel. And hopefully I'll see a few of you in office hour. Have fun hacking away, everybody. Talk to you soon.